All right, in this lesson, we're going to learn about percent composition and how it works as you apply it to chemicals and how chemistry uses those to figure out more stuff. One of the more important things, sometimes often the most difficult, we'll get to that part later, aspects of chemistry is figuring out what's exactly in a substance. And so a lot of times we focus a lot on percent composition. All right, the first one we're going to introduce here is that we're going to look at percent composition from experimental data. All right, that's nice and bolded. We'll see how that word becomes important. But broadly speaking, I think you'll recognize that a percent is always going to be a part over a whole. And so you see that over here in this formula, you got the part that is part of that's part of the compound, right? So the element that is relevant, and we divide it by the mass of the entire compound, part over whole. And if you know the element's mass, you can divide it by the entire compound's mass. So let's see this example here, a sample of compound with magnesium. And nitrogen contains 9.03 grams of magnesium and 3.48 grams of nitrogen. What's the total percent composition of magnesium and nitrogen? All right, so in this first step, total mass of compound, as you can imagine, right? This is a pretty straightforward step. You take these two masses of each element, you combine them, and that gives you the mass of the entire compound. That mass of the entire compound now can be used for this bottom denominator. So then the total composition of magnesium, the work would look like this. You can probably do like percent Mg is equal to the mass that's relevant to magnesium. That's 9.03 grams of Mg. And then as a denominator, you can maybe just broadly say 12.51 grams of just compound. Right, do a little bit of math and you'll see that your result here becomes 72.2% following the significant figures and so on and so forth. And now for the percent composition of nitrogen. Well, we have a couple of options here. You can go through the same method we did a minute ago. So percent N, that's equal to 3.48 grams of nitrogen divided by the 12.51 grams of compound. That's that word compound in there. And do the math that way, and that gets you an answer of 27.8%. Now, the alternative really is because it's a percent composition. The percent's always going to be 100 when you add them all together. And so for this one, if you do 100 minus 72.2%, you end up getting 27.8%. Done. So in either method, you would get the same result. And the important thing is that you are keeping track of which one goes to which. And for the sake of just some follow through, right, we'd say 72.2% that's magnesium, 27.8% that's nitrogen. Naturally, it's always good to double check your math. You either add up to 100%, especially if you go with kind of the two right here that require those individual formulas rather than just subtracting from 100. What type of graph might you want to use here? Probably a pie chart, maybe a circle graph, whichever one you probably are used to. But that's a good one because then it kind of represents exactly, just visually, what the breakup is, right? So we say this much is going to be your magnesium, and then maybe this much is your nitrogen. That's sometimes going to be useful in interpreting how we go with the next step. In this next one, testing your understanding here, it says a 7.055 gram sample of that same magnesium and nitrogen compound is analyzed, right? So we have the same compound, but it's a different amount. Address the following questions. Number one, what's the percent magnesium and percent nitrogen in this compound? All right, well, notice how we're not given amounts of either magnesium or nitrogen. But also remember, we should know that the percentages are always going to be the same, right? Anytime you have a compound, it is known that the percentages are always going to be the same. That's how we know that these compounds have certain formulas and so on and so forth. So really, they should be the 72.2% magnesium and then the 27.8% nitrogen from before. These should always be the same. No matter how big or small your actual given sample is, these percentages will always be true. What mass of magnesium and nitrogen are in this compound? We're basically going to take that formula and work a little bit backwards, right? So we have percentages. Let's start with magnesium, 72.2%. That's going to equal to some X amount of magnesium divided by, I can probably just say X there, right? Let me go back here, put the magnesium in there. So that's equal to X over the total amount, which is 7.055 grams of this compound, whatever it is. So then I can rearrange it and solve for x. So where x is equal to 5.09 grams of magnesium. Now we're going to have to do a little bit of significant rounding here, significant figures rounding, since this one has 4 in this number right here. This one's going to be 3 significant figures. So multiplying those two out kind of limits you in terms of numbers of figs. 5.09 grams of magnesium is all we can do. And at this point, again, you have two options. So we can go ahead and take nitrogen and reapply that formula. So we can do the whole setup of 27.8% nitrogen. That's going to be equal to x of nitrogen divided by the 7.055 grams of compound, and then solve for x. Alternatively, you can take the total of 7.055 minus the 5.09. Either way, that'll get you the same answer of 1.97 grams of nitrogen. And that's basically how that works, right? So in this case, notice how we're talking about the percent composition in this section using masses, right? Using experimental data. And that's what this was about up here. So all of that is when you're given actual numbers from the mass. But in this case, we're going to try another type. This is going to be the second one. In this case, we're going to do percent composition just from chemical formula. All right, so chemical formulas, this time you'll not be given any masses. You'll just be given a formula and you have to figure out the rest of it. But in this case, right, we might be confused about as to how we can get any numbers, but we actually can use the molar mass instead, right? If you remember, the molar mass are those numbers from the periodic table. So in using those, we can actually get a lot of information. So let's take a look at the first example. What's the percent composition of bromine in hydrobromic acid? All right, well, given hydrobromic acid, you can see there, it would help to actually have the formula. So let's go ahead and formalize that. That's going to be HBr. And from here, we got to do a little bit of work. We got to then say, okay, I know that I don't have any masses, so I have to use the molar masses from the periodic table. I know that pulling the number from the periodic table, that number for hydrogen is 1.008. Br is going to end up being, let's see, 79.90. Both these are in grams per mole. And kind of thinking about this and planning ahead, I'm also going to have to get the molar mass of the entire compound, so I can add these two together. And that's going to end up giving me a value of 80.91 grams per mole of the compound. So what's the percent composition in this case? It's just bromine, percent Br. That's equal to 79.90 grams per mole Br, right? This time again, we're not just doing grams, right? We have to be doing this in molar mass. Divided by the total molar mass, which we just figured out a minute ago, is 80.91 grams per mole of HBr. And then we can do a little bit of math. The percent that is bromine will end up being 98.75%. All right. And that's basically it. And that's how the setup is, this time using chemical formulas. In this case right here, determine the percent composition for oxygen and sodium nitrate, right? So this guy right here. This time it's a little bit more complicated, but we still follow the same process. I still care about percent of oxygen. And what I'm going to do is I can do a couple of things here. Since, you know, oxygen individually is 16, I'm just going to honor the fact that there's 3 of them total. So 16.00 grams per mole of oxygen. And then divided by the entirety of the thing. So in that case, I can do this off to the side if you really want to, but just for the sake of having the right numbers, 99. Nitrogen is 14.01. Oxygen is going to be 3 times the 16.00. And that ends up having a total sum of 85.00 grams per mole. So I take that, toss that under here, 85.00 grams per mole of NaNO3. Again, we're talking about molar masses overall. So we can then plug this in our calculator, remembering, of course, to multiply the 3 times the 3 oxygen molar masses that are there, because the formula has 3 of them. And eventually, getting a little bit of math out, you do 56.47%. Oh, just to be clear, we are looking at the fact that we have 4 significants out of this, and we have 4 significant figures out of that. So this one also should have 4 significant figures when you multiply and divide. Keeping this going, we have the application of percent composition. So this time we kind of have already done it, but this time we're going to use this when I'm just sort of given amounts of information. So whatever the case, right, the percent composition, it can always be determined through several methods, right? One method through experimental masses, the other one through molar masses, or through just the compound formula, which we just did. Regardless of the method, the percent composition must be the same. Because of what principle? Right. So again, no matter how we get it, no matter what we do, no matter how we approach these problems, the percent composition must always be the same because of the law of definite proportions, right? These proportions, these percentages are always going to be the same. Proportions, I think that's how you spell it. So the law of definite proportions basically says that no matter how we get these samples, no matter what we do to them, these samples are always going to be the same percentage, because otherwise these compounds wouldn't be defined, right? We have to define these compounds as saying these have certain ratios. These are it. So let's go and take a look. We have obtained a sample of potassium nitrate. It has a mass of 80.55 grams. Through some percent composition skills, you determine that 38.67% of potassium nitrate is just the potassium ion. What's the mass of potassium in your sample? Mass of potassium. So let's see this. We got the 38.67%. That is your potassium nitrate, right? But then 38.67% of that is the potassium ion. You can add a little plus there just to remind yourself that it is the ion. And it's going to be equal to the total mass on the bottom, which is going to be 80.55 grams of this compound. Since we know the formula ends up being KNO3, I can do that. And then you do a little bit more here just to say that, hey, I don't know that value yet, so I can rearrange and solve for it. So doing algebra however you choose, you can solve for x. And again, it's very similar to what we've done before. But for the sake of just following through, you can see that 31.15 grams of ions. What makes this problem pretty straightforward is that they pretty much give you everything you need, right? There's the formula that you can use using experimental masses. I have a percentage that's provided to me. I have a total mass of the compound, which is provided to me. So out of the three things here, I have this last one, which I can then just solve for. But let's look at the next one here. What's the mass of chlorine in a 110 gram sample of copper 2 chloride? Right, for the sake of just speeding things along, this is going to be CuCl2. All right. So in this case, right, kind of comparing these two problems here, I'm not given a percentage that is chlorine. I'm only given the total amount of the compound. So that's the denominator of this formula. So I don't have a percentage here. But here's the thing though, I am given a formula. So isn't there a way I can get the percent that is chlorine somehow out of this guy, right? If I have the percent that's chlorine, I can just do what I did in example 1 basically and solve for the amount of chlorine, right? The actual amount, the mass of chlorine. But since I don't have that, I got to work around a separate way. So I know I have the formula here, CuCl2. Let's do this. We're going to now use the percent composition by formula by doing chlorine. So in this case, CuCl2, I know that there's going to be 0.45 grams per mole of chlorine. And then the bottom part, basically just add up copper and chlorine from the periodic table. Copper is 63.55, so on and so forth. So the total ends up being 134.45 grams per mole of copper chloride. And then now this gives us a percentage. This percentage ends up being 52.73%. All right. But that's not really what the question's asking for. What this does, though, is it allows us to basically have, like example 1 here, a percentage that we can work with, which we can then apply to the given mass in this problem. So let's rewrite it. 52.73% is going to be equal to the entire mass, which is 110 grams of CuCl2. Again, this Cl, I forgot to label that. And then on top I have the x, just like the previous problem up here. So I know that I can rearrange, solve what I need to. And then my final answer ends up being 58.0 grams of Cl. And that's your final answer. So this one takes a little bit more work, but again, the principles are still the same. I know that my law of definite proportions allows the percentage to always be the same. If I have the formula, which got to sometimes do a little work for, as long as I have the formula though, I can get a percentage. So any given mass, whatever it might be, that mass can have a percentage that you can figure out. Finally, we're going to do percent composition of a group. So percent composition of a group here is very similar. Just got to be careful about how you add the numbers. So for example, we're going to see that sometimes we want percent composition of a group of elements in a compound. So in this case, what is the percent composition of cyanide in the compound ruthenium-3 cyanide? All right, so once again, given an equation here, given a term, a word, let's go ahead and get to a formula. So in this case, it's going to be RuCN. 3. So Ru and then Cn3. And then the total molar mass for this guy ends up being 179.13 grams per mole for the whole thing. All right, speeding along things. So how do you get the percent composition of that cyanide? Well, percent composition of cyanide, that's going to equal to the part that is cyanide. So in this case, we have 3 of them, so I'm going to do 3 times. And then the group altogether is collectively carbon and nitrogen, so 12.01 grams per mole plus nitrogen, which is 14.01 grams per mole, like that, all right? Again, I'm simply honoring the fact that you have to take those from the periodic table. If you want to go ahead and add those 2 together ahead of time to make it one value up here, you can, right? That's not a big deal. I trust that you can take the numbers off the periodic table appropriately, but in this case, it would be 26.02 grams per mole if you decided to go that route. And then like I said on the bottom, we've already done this 179.13 grams per mole of RuCN3. All right, then do a little bit of work. In this case, making sure you plug the numbers in appropriately, round accordingly, and your final answer of %Cn minus is equal to 43.58% Cn minus. All right, and through all of this, make sure that you are being careful about significant figures. And of course, one thing I haven't really been doing a lot is showing that step where you multiply it by 100 or changing a percentage into a decimal. But I trust that you can do that on your own. Otherwise, that'll do it.